A longitudinal assessment of running economy and tendon properties in long-distance runners. Longitudinal assessment of running economy and tendon properties in long-distance runners. Journal Strength and Conditioning Research 1724 through 1731, 2010. The aim of this study was to investigate longitudinal changes in tendon properties and running economy of long-distance runners, LDRs. In the preparatory periods of track season, TS, and road season, RS, 11 well-trained LDRs and 6 untrained subjects participated in the present study. In each period, muscle strength, neural activation level, and tendon elongation for both knee extensors and plantar flexors, jump performances, and oxygen consumption during submaximal running velocities were measured. No significant differences observed in any measurable variables between the two seasons for untrained subjects. For LDRs, the total running distance during 1 month preceded RS, 832 plus or minus 95 kilometers, was significantly longer than that during 1 month preceding TS, 718 plus or minus 80 kilometers. No significant differences in the muscle strength, neural activation level, and jump performance were found between TS and RS. The stiffness of tendon structures in RS were significantly lower than those in TS for both knee extensors, negative 14.4%, and plantar flexors, negative 16.6%, at 3 running velocities. The oxygen consumptions in RS were significantly lower than those in TS. These results suggested that the lower oxygen consumption during submaximal running velocities observed in the preparatory period of RS may be attributed to the more compliant tendon structures, but not in the neuromuscular characteristics. Introduction. Some previous studies indicated that running economy defined by the steady-state oxygen consumption for a given running velocity contributed to distance running performance among trained athletes. According to some previous findings, there were no significant changes in running economy during 1-year training cycle. In contrast, other researchers reported an improvement in running economy and performance over a 1-year training cycle. However, a few studies have investigated the changes in running economy of the well-trained long-distance runners, LDRs, among the different phases of the training cycle. It is well known that the well-trained athletes change the training volume and intensity throughout the training cycle for improving their performance at each event. Therefore, information on the changes of running economy among the different phases of training cycle is essential for improving the performance of LDRs. Recent studies have used ultrasonography to investigate the effects of tendon properties on the performance during stretch shortening cycle exercises. Staphylidis and Arampatsis reported that the tendon structure in knee extensors were more compliant in excellent sprinters than that of inferior sprinters. Therefore, it is likely that the running economy in long-distance runners would be related to the tendon properties. Indeed, Arampatsis et al. Showed that the knee extensors of most economical runners had a more compliant tendon and aponeurosis. Considering these previous findings, we hypothesize that if the running economy of well-trained LDRs changes among the different phases of the training cycle, these changes would be related to the tendon properties in lower limbs. In the present study, we investigated the tendon properties and running economy in the different phases of training cycle in terms of training volume and intensity, that is, preparatory phases of track season, TS, and road season, RS. The purpose of the study was to investigate longitudinal changes in tendon properties and running economy of well-trained LDRs in the different seasons. Methods. Experimental approach to the problem. According to some previous findings, the running performance and economy of LDRs improved with resistance and plyometric training. However, the detailed mechanisms of change in running economy because of an additional resistance and/or plyometric training are unknown. On the other hand, recent studies demonstrated that the tendon properties affected the performance during stretch shortening cycles exercises, that is, jump, sprint, and distance running. Considering these points, we examined the tendon properties and running economy of well-trained LDRs in the different phases of the training cycle in terms of training volume and intensity. From these findings, we aim to get to the fundamental knowledge for planning, training, and improving the performance of LDRs. Subjects. 11 well-trained male LDRs participated in this study. However, 3 subjects could not perform the measurements of jump performances and running economy in the preparatory phase of RS. See below. The reasons given were injury of left leg, and lower back pain. Data are therefore presented for 8 subjects, jump performances and running economy, and 11 subjects, other measured variables. The duration of training experience ranged from 5.9 to 11.1 years, 7.7 plus or minus 1.5 years. The best official record of the LDR, a 5,000 meter race within 1 year before these tests, ranged from 14 minutes 11 seconds to 14 minutes 53 seconds, and the average was 14:33 minutes to seconds. Throughout 1 year, LDR ran from 150 to 100 kilometers a week on average, at least 6 days a week, and up to 4 hours a day. In addition, 6 untrained individuals whose age, body height, and limb lengths are similar to those of LDRs were selected as a control group, CRL. The physical characteristics of all subjects, LDRs and CRL, were shown in Table 1. All CRL subjects were either sedentary or mildly active, but none were involved in any type of regular exercise program for at least 1 year before the test. All subjects were advised to maintain their usual dietary habits and not to make any intentional changes, such as increasing the amount of intake or number of meals per day to avoid nutritional influence. The study was approved by the Faculty of Physical Education, Kokushikan University, and was consistent with their requirements for human experimentation. All subjects were fully informed about the experimental procedures to be used and the purpose of the study, and were given written informed consent before participating in the study. Procedures. Experimental design. The measurements of muscle function and tendon properties, see below, were performed on the right lower limb. Subjects had previously visited the laboratory on at least one occasion to familiarize themselves with the procedures involved. The preparatory period of TS was characterized by a decreasing training volume, i.e. running distance, and increasing training intensity, i.e. running speed. In the preparatory period, RS and LDRs aimed to increase the running distance mainly. For LDR, the measurements were performed in the preparatory periods of track season, the first 10 days of May 2008, and road season, the first 10 days of September 2008. In the present study, we planned that for each subject, a time slot measurement for TS was consistent with that of RS. Long-distance runners recorded the distance of running per day and totaled the distance of running during 1 month preceding the measurement. For CLRs, these measurements were performed at the same time. Body composition. Body mass was measured, the nearest 0.1 kilogram using a calibrated scale, and height was measured to the nearest 0.1 centimeter. Percent body fat was assessed using the segmentary multi-frequency bioelectrical impedance analysis performed within in-body 2 machine, Biospace Tokyo, Japan, according to the procedure described by Kiyama et al. Muscle strength. Maximum voluntary isometric torque, MVIT, was measured by means of specially designed dynamometers. Applied Office, Tokyo, Japan, for knee extension and plantar flexion, respectively. Torque signals were amplified, sampled at 1 kilohertz using a 16-bit AD converter, Power Lab 16SP, ADI instrumentation, Sydney, Australia. All measurements were performed on the right lower limb. During each task, subjects exerted isometric torque from 0, relaxed, to MVIT within 5 seconds. During the knee extension task, subjects sat in an adjustable chair with support for the back and the hip joint flexed at an angle of 80 degrees. Full extension is 0 degrees. To standardize the measurements and localize the action to the appropriate muscle group during torque measurements, the hips and the back were held tightly in the seat using adjustable lap belts. The axis of the knee joint was aligned with the axis of the lever arm of the dynamometer. The right ankle was firmly attached to the lever arm of the dynamometer with a strap and fixed with a knee joint flexed at an angle of 90 degrees. Full extension is, of course, 0. During the plantar flexion task, subjects lay prone on a test bench, and the waist and shoulders were secured by an adjustable lap belt and held in position. The ankle joint was set at 90 degrees with the knee joint at full extension, and the foot was securely strapped to the foot plate connected to the lever arm of the dynamometer. Before the test, subjects performed a standardized warm-up with submaximal contractions to become accustomed to the test protocol. Each task was repeated 2 or 3 times per subject, with the last 3 minutes between trials. The highest value among these trials was recorded as the muscle strength for each. We performed the measurements of all the items, strength, tendon properties, activation level, see below. For knee extensors first, and then for plantar flexors. At least a 10-minute rest period was inserted after the measurements for knee extensors. Elongation and stiffness of tendon structures. Elongations of the tendon structures, knee extensions, and plantar flexors were also assessed during isometric knee extension and plantar flexion. The task was repeated 2 times per subject with at least 3 minutes between trials. The measured values shown below are the means of the 2 trials. An ultrasonic apparatus, SSD 2000, Aloka, Tokyo, Japan, with an electronic linear array probe, 7.5 megahertz wave frequency with an 80 millimeter scanning length, UST 5047-5, Aloka, was used to obtain longitudinal ultrasonic images of vastus lateralis at the level of 50% of their length, that is, distance between the greater trochometer and the lateral epicondyle of the femur and the medial gastrocnemius muscles of the level of 30% lower leg length. That is, the distance between the popliteal crease and the center of the lateral malleolus. The probe was longitudinally attached to the dermal surface with adhesive tape, which prevented the probe from sliding. The ultrasonic images were recorded on videotape at 30 Hz and synchronized with recordings of a clock timer for subsequent analysis. The point at which the fascicle was attached to the aponeurosis was visualized on the ultrasonic images. This point moved proximally during isometric torque development up to the maximum. See Figure 1 of reference 8. The displacement of this point is considered to indicate the lengthening of the deep aponeurosis of the distal tendon. And the displacements of the tendon and aponeurosis will be attributed to both angular rotation and contractile tension, because any angular joint rotation occurs in the direction of the knee extension and plantar flexion during the isometric contraction. Thus, angular joint rotation needs to be accounted for to avoid an overstimulation of tendon displacement during the isometric contraction. To correct the measurements taken for the tendon and aponeurosis elongation, additional measurements were taken under passive conditions. To monitor joint angular rotation, an electronic gynometer, Penny and Gallus Biomechanics Limited, Gwent, United Kingdom, was placed on the lateral aspect of each joint. The displacement of each site caused by rotation of the knee and ankle from 110 to 70 degrees was digitized in sonographs taken. Thus, for each subject, the displacement of each site obtained from the ultrasound images could be corrected for that attributed the joint rotation alone. In this present study, only values corrected for angular rotation are reported. The measured torque, TQ, during isometric knee extensions and plantar flexion was converted to muscle force by the following equation, where K is the relative contribution of physiological cross-section area of each vastus lateral muscle within the knee extensors and medial gastrocnemius muscles within the plantar flexors, and MA is the moment arm length in each of the quadriceps femoris muscles at 90 degrees and triceps surae muscles at 90 degrees, which was estimated from the limb length of each subject. In the present study, the force and the tendon elongation values above 50% of MVIT were fitted to a linear regression equation, the slope of which was adopted as stiffness, e.g. 14. Intraclass correlation coefficient, ICC, and means of coefficient of variance, CV, of the two measurements were 0.89 and 6.9% for knee extensions and 0.91 and 7.4% respectively. Resting twitch properties and neural activation level. The posture of the subject and setup were the same as those for the measurement of the muscle strength and tendon properties as mentioned above. At least a 5-minute rest period was given after measurement of the tendon properties. Resting twitch properties were assessed by supramaximal electronical stimulation. The task was repeated 2 times per subject with at least 2 minutes between trials. The measured values shown below are the means of the 2 trials. The stimulating lead electrodes were placed on the skin over the femoral nerve at the inguinal region, and the midbelly of the quadriceps femoris muscles for knee extensors, and on the skin of the right popliteal fossa and orientated longitudinal to the estimated path of the tibial nerve with the anodistal for plantar flexors. A high voltage stimulator, SEN 3301, having a special modified isolator SS1963 Nihon Koden, Tokyo, Japan, generated rectangular pulses, triple stimuli with a 500 microsecond duration for one stimulus, and an interstimulus interval of 10 milliseconds. Maximal twitch contractions were evoked in the resting muscle by progressively increasing the stimulation intensity until the increase failed to elevate twitch torque further. The stimulus intensity that elicited peak twitch torque was used throughout the duration of the measurements. Peak torque time to peak torque and half relaxation time were measured as the twitch properties. When the voluntary torque peaked and superimposed maximum triple twitch was applied to assess the activation level of the muscles. The difference between the peak twitch torque and the MVIT twitch torque was measured. Shortly, within 1 to 2 seconds after MVIT, the same stimulation was given to the muscle at rest, control twitch torque. The measured values shown below are the means of 2 trials. The neuroactivation levels, percent of the knee extensor muscles, was calculated as 1 minus twitch torque during MVIT divided by control twitch torque times 100 as previously reported. Intraclass correlation coefficient and CV of the 2 measurements were 0.89 and 2.3% for peak torque, 0.91 and 2.1% for time to peak torque, 0.87 and 2.5% for half relaxation time, and 0.85 and 3.2% for neuroactivation level, respectively. Jump performances. Each subject performed 2 kinds of maximum vertical jumps on the force plate, Kistler 9281B, Winter Thur, Switzerland, and without counter movement, that is, the counter movement jump, CMV, and squat jump, SJ, respectively. Subjects retained the hands on hips position until the final phase of jumps. For the SJ, subjects were positioned on the force plate with a knee angle of 90 degrees. For the CMG, subjects stood erect and counter-moved until the knee was flexed to 90 degrees before jumping. For all trials, subjects were instructed to jump as quickly as possible to a maximum height. The angles were accurately controlled by the use of an electroneometer. Penny and Gillis were excluded to the trials in which the extra dip saw just before jumping of SJ and knee angle differed by plus or minus 5 degrees for the lowest position of CMG. By measuring the flight time from the force record, the vertical takeoff velocity of the center of gravity and jump height of the center of gravity were calculated as follows, where g is the acceleration of gravity. The test was repeated 5 times per subject, except for the trials in which knee angle differed by more than plus or minus 5 degrees, with at least 3 minutes rest between trials. 3 data, excluding the largest and smallest values, were averaged. Coefficient of the variation of the 3 measurements were 5.3% for SJ and 4.7% for CMJ, respectively. The performance during stretch shortening cycle exercise was evaluated from the relative difference in jump height between SJ and CMG as an augmentation by the prior stretch. Pre-stretch augmentation is percent equals CMJ minus SJ times SJ minus 1 times 100. Running economy was determined by measuring oxygen consumption, milliliters a kg per minute, at the 3 different velocities on a treadmill, AR 100, Minato Medical Science, Osaka, Japan. For LDR, after a warm-up period of 4 minutes at a running velocity of 10 kilometers an hour. The subjects ran at 3 submaximal velocities, 14, 16, and 18 kilometers an hour, for 4 minutes. For CRL, after a warm-up period of 4 minutes at a running velocity of 6 kilometers an hour, the subjects ran at 3 submaximal velocities, 8, 10, and 12 kilometers an hour for 4 minutes. Oxygen consumption was measured during the 4 minutes of each running velocity using a breath-by-breath spirometer, AE 3005, Minato Medical Science, Osaka, Japan, and the average value of the oxygen consumption was calculated during the last minute of each running velocity. The repeatability of the running economy oxygen consumption at 3 different velocities measurements was investigated on 2 separate days in a preliminary study with 5 young men. Interclass and correlation coefficients and CV of the 2 measurements were 0.84 and 5.1% for 8 kilometers an hour, 0.87 and 4.7% for 10 kilometers an hour, and 0.83 and 6.5% for 12 kilometers an hour, respectively. Statistical analysis. Values are reported as means, percent standard deviation, by a two-way analysis of variance with repeated measures. Two groups times 2 test times was used to detect the significance difference in the measured variables between TS and RS. The level of significance was set to less than or equal to 0.05. Power calculations, statistical power, were performed using G times power computer software. Statistical power greater than 0.8% was obtained in the main significant changes, for example, stiffness, etc. Results. The total running distance during 1 month preceding RS, 832 plus or minus 95 kilometers, was significantly longer than that during the 1 month preceding TS, 718 plus or minus 80 kilometers. 12.7% deviation error, 0.005. Effect of size, ES equals 1.31, figure 1. There were no differences in body mass and present body fat between TS and RS, table 1. For both knee extensors and plantar flexors, MVIT activation levels and twitch properties, peak torque time to peak torque and half relaxation time, did not show any change between TS and RS, table 2. For both knee extensors and plantar flexors, the elongation values of tendon structures in RS were significantly greater than those in TS, figure 2. The maximum elongation values of tendon structures in RS were significantly greater than those in TS, knee extensors, plus 23.1%, deviation of error, 0.008, ES equals 0.69, plantar flexors, plus 12.8%, deviation of error, 0.005, ES equals 0.82, figure 2, table 2. The stiffness of tendon structures in RS was significantly lower than that in TS for knee extensors, negative 14.4%, deviation error, 0.023, ES 0.76, and plantar flexors, negative 16.6, 0.040, ES 0.65, figure 2, table 2. Both SJ and CMJ heights tended to be lower in RS. SJ 23.3 plus or minus 3.6 centimeters, CMJ 24.6 plus or minus 3 centimeters, then in TS 24.1 plus or minus 2.6, CMJ 25.3 plus or minus 2.8, SJ deviation error 0.150, CMJ 0.061, figure 3. There were no differences in the pre-stretch augmentation between TS 5 plus or minus 4.7% and RS 6 plus or minus 4.9%. Probability of error 0.493. At 3 running velocities, the oxygen consumption in RS were significantly lower than those in TS, figure 4. The measured variables for CRLR were presented in tables 1, 3, and 4. No significant changes in all the measured variables were found between TS and RS. Discussion. Main finding of the study was that oxygen consumption during 3 running velocities decreased significantly in RS compared to TS. This result implied that when the training volume, total running distance, increased, the running economy improved for the well-trained LDRs. Recent studies demonstrated that the running performance and economy improved because of an additional resistance and/or plyometric training. Up to now, however, the detailed mechanism of changes in running economy because of an additional training are unknown. Pavlinin et al. Reported that simultaneous explosive strength and endurance training produced a significant improvement in 5-kilometer running performance in LDRs. In addition, they stated that these improvements were because of improved neuromuscular characteristics that were transferred into enhancing muscle power and running economy. In the present study, however, no significant changes in muscle strength, activation level, and twitch characteristics between TS and RS. Therefore, we may say that the improved running economy in RS was not related to the neuromuscular characteristics as stated by Pavlinin et al. Other interesting finding of the study was that the tendon structures for both knee extensions and plantar flexors were more compliant in the preparatory period of RS than in the preparatory period of TS. Our previous studies demonstrated that the human tendon structures did not change after repeated ballistic exercises. Example, drop jump. Temporarily. Furthermore, DZ et al. Showed that the tendon of pig hardly changed during the dynamic loading such as running, referred to as dynamic creep. Therefore, the present result conflicted with these previous findings concerning acute changes in the tendon properties in vivo and in vitro. On the other hand, fatigue leads to failure after repeated applications of stress, which may be much lower than that ultimate stress. Some previous studies showed that mean extensors of tendons increase slowly during the fatigue test but much faster just before rupture. Wang et al. Implied that this failure would result from cumulative damage in the present study. The difference in the total running distance was almost 100 kilometers, about 13% between TS and RS. Assuming that the stride length of one step is 1.5 meters, we can say that the repeated number of steps in the RS increased about 67,000 steps compared to that in TS. This amount of increase in steps would be considerably greater than that of DZ et al., corresponding to the running of 20 minutes with the speed of 19 kilometers. 3% strain, 1,600 cycles. Certainly, the differences in the materials of the surface, track versus road, would affect the tendon properties of lower limbs. However, it is very difficult to mention this point because LDR in the present study ran on both track and road in TS and RS indeed. In the present study, we would like to pay attention to the difference in the total running distances. Considering these points, it may be that the observed increase in the tendon elongation is related to the cumulative damage of tendon structures because of the increase in training volume, i.e. running distance. Recent studies using ultrasonography demonstrated that the performances during stretch shortening cycle exercises were related to the tendon properties. As mentioned above, the maximum elongation of tendon structures for both sites in RS increase in total running distances were longer than TS. Apart from the fatigue of tendon structures, it is likely that the increment of tendon extensibility in RS is related to the improvement of performance during stretch shortening cycle exercises. Indeed, Kubo et al. And Stefalides and Arampatsis reported that the tendon structure in knee extensors were more compliant in excellent sprinters than that of inferior sprinters. Moreover, Arampatsis et al. Showed that the knee extensors of the most economical LDRs had a more compliant tendon and aponeurosis. Therefore, the present results support the above previous findings. Considering these points, the changes in tendon properties would contribute to the improvement in running economy in the preparatory periods of RS. These discussions are speculative and require additional data for clarification. The practical applications. We investigated longitudinal changes in muscle and tendon properties, jump performances, and running economy of LDRs in the preparatory periods of TS and RS. The present results indicated that the lower oxygen consumption during submaximal running velocities observed in the preparatory period of RS may be attributed to the changes in tendon properties, but not in the neuromuscular characteristics. Furthermore, because the jump and running exercises included stretch shortening cycle of lower limb muscles, we expected that the changes in jump heights were linked with the changes in oxygen consumption during submaximal velocities, running economy. However, there were no differences in jump performance between the two seasons. Taken together, these results implied that the LDRs, it should be adopted running exercise, but not jump exercise to evaluate abilities of stretch shortening cycle exercises certainly. Acknowledgements. This study was supported by the Grant and Aid for Exploratory Research 196501682K Kubo from Japan Society for Promotion of Science. The authors would like to thank all the subjects who participated in this study for volunteering their time and energy.